So this is a joint work with Neria Sidorovas, who is a current PhD student, co-supervised with Dmitry Tseluika, a colleague from Loughborough. And we also collaborated on that with William Choi, who fortunately also in the room today. Neria's PhD is funded by EPSRC. So I always admired the stuff that is done by Jean-Marc and his students. It's always very interesting and always fun, right? And it transpired as when I was preparing to this talk and trying to find Jean-Marc's photo, I realized that this was spotted by BBC. And at some point, it was reported that SciTech professor spilled secret of the dripping teapot. So Jean-Marc, happy birthday, and I hope that we will have lots of beautiful results and fun from you as usual, not only in the next 20 years, but beyond that.
Thank you, Karima.
Okay, so here is a brief overview of my talk. We had a lot of exponential asymptotics and a little bit of KDV in the very first talk. So we are back to KDV in this last talk of today. Although it will not be the usual KDV, it will be a cylindrical quarter-vector phase equation and related stuff. So here is an outline. I will begin with a brief introduction and motivation. The context of the numerics that I'm going to discuss today is axisymmetric 2D Boussinesq system. So I will show you some numerical experiments that we have done trying to compare 2D Boussinesq and cylindrical quarter-vector freeze type models. And hopefully, time permitting, I will finish with some analytical results and open questions that are related to this kind of models. So the cylindrical or concentric quarter-vector freeze CKDV equation looks like that. Okay, so the first three terms KDV, but there is this cylindrical divergence term, the last term, which obviously changes the dynamics. And similarly to the KDV, it's a universal weakly nonlinear weakly dispersive wave equation in cylindrical geometry. I used to think that the first people to introduce it were Maxson and Vicelli for waves in plasma, but Yuri Stepanyan's has sent me a paper by Iordansky from 1959, where indeed the equation is written, although it's not in these variables, right? So it's in characteristic variables actually. And if you change variables to what we have now, it's kind of an asymptotical equivalent version, but it looks exactly the same like this equation. Although he didn't derive it by using any asymptotic analysis, he did it as physicists do, right? Kind of, this is small, this is large, and so on. So in the context, it was suggested in the context of water waves, potential formulation, and derivations for surface waves in a homogeneous fluid in the context of Boussinesq system were by Miles in 1978 and by Robin Johnson in 1980 from the full Euler equations. So I will also mention internal waves, although most of my talk will be about surface waves. But in 1985, Lipovsky and 92, Weidman and Villard derived the CKDV equation for internal waves in a stratified fluid with no shear flow, using the same modal decomposition as for the plane waves, which exist in that case. In 1990, Johnson obtained a CKDV type equation for surface waves in a homogeneous fluid on a shear flow. And in 2016, with my PhD student, Xizhong Zhang, we obtained a description of internal and surface waves in a stratified fluid on a shear flow, a generalization of this Johnson's paper from 1990. So when there is a current shear flow, depth-dependent parallel shear flow, there is no modal decomposition. That's the difference with the situation when there is no current and with the plane waves. However, what we managed to show in this paper and what has has led to the subsequent developments was the existence of the model decomposition in the far field, okay? And because the models of that kind are far field models, then actually this is enough for development of the models of I gave a talk on this in Bath in the conference organized by Paul in Bath last year. So therefore, I will not repeat it. I will just highlight a couple of interesting effects which take place. So this is actually from the same paper with Sejong in 2016, where we considered as an example. So the theories for the arbitrary stratification and arbitrary depth-dependent parallel flow, and essentially it consists of the set of model equations, which contain a spectral parameter, and this spectral parameter is a dependence on the polar angle, which essentially knows about the wave velocity in different directions, right? Because there is a current, wave propagates with different speeds in different directions, and there is a nonlinear first order ordinary differential equation, which we now call angular adjustment equation, which essentially plays the role of a linear dispersion relation in this setting, long wave dispersion relation. So the interesting phenomenon which we found in the context considering this example of a two-layered fluid with a piecewise constant current was that the wavefronts of the surface waves are elongated on the current as the current strengthens, which is intuitive, something that we see when we look, for example, on a river flow or something like that. But the wavefronts of internal ring waves on the same current are squeezed, okay? So in the direction of the current. And we realized that this is related to the existence of the long wave instability in the system, which was discussed by Ovsyannikov and then by several other authors. So, and as the parameter, the strength of the current approaches the critical value, when these branches for internal, so these are surface waves, co-propagating, counter-propagating, and the green and blue curves are the velocities of internal waves, right? So as we approach this critical value of the strength of the current, when the two branches coalesce, this is when we see the squeezing of the internal ring. So later on, we managed to extend this to two-layered fluids with a rather large family of currents, two-parameter dependent, which could have either this curvature or the opposite curvature, depending on the value of the parameter alpha. And it is possible to show that this behavior is structurally stable. And for some values, so essentially for these types of currents, when there is some flatness, yeah, it's not piecewise constant current, but there is always some value of alpha when we will see a similar phenomenon. And the most recent development, I show you just one picture, for three-layered fluid on a linear current with a rigid lid on the top. This was done in collaboration with Dmitry, Ricardo, who is here, and our student. So in that case, we have observed and discussed that the first mode, the wavefronts of the first internal mode are elongated in the direction of the current, but the wavefront of the second internal mode is squeezed in the direction of the current. And again, it was shown that this is related to the existence of the long wave instability for the second mode. So this paper is due to appear shortly in Nonlinearity. Okay, so we continue to work on that, waves on currents, currently working on hybrid waves consisting of a part of a ring wave and two tangent plane waves. Hope to report these results to you shortly, but today I would like to take this in a different direction. So models of KDV type are, of course, weakly nonlinear models, and they work for small values of parameter epsilon. However, it has been known in the community and certainly believed that extending these models to so-called extended quarter-vector equations, like this is how it looks like for the plane waves, for example, right? If we just account for the next order terms, might make it work for waves of great amplitude, okay? Originally, the model, I think it was initially, the first paper was Coop and Butler, it certainly was done for the situation when the parameter alpha is small, and then it's natural that you can include the high order cubic nonlinearity and then all terms of the same order. But it's not the situation that I'm interested in. Okay, I'm interested in the usual situation where KdV is relevant, alpha is not small, and the question is, does it help to add order epsilon terms to the equation? Does it work for the waves of moderate amplitude? Okay, can we go further in epsilon? So this is how the equation looks like for the plane waves. Horikis, Franciskakis, Marchand, and Smythe. Noel Smythe, unfortunately, has died very recently from cancer. So they have derived in one of Noel's latest papers, they have derived this version of the extended cylindrical quarter-vector phase equation. This is the so-called slow time version of the equation, okay? That's how it looks like. There is a non-local term. They assumed, my understanding is they assumed that there are no waves at the origin, okay? We will assume that there are no waves at infinity. We think that this is a bit more practical. So essentially the questions are, is an extended CKDV equation a better model for the waves of moderate amplitude, and how to use it for practical purposes if we want to solve initial value problems? So we are not as good in doing numerics as Jean-Marc, so we settled at the setting of 2D Boussinesq system. Two small parameters, amplitude, long waves parameters. We use the maximum balance condition, familiar, right? Numerics is done in the moving reference frame. So psi is r minus t. And rewriting the 2D Boussinesq and cylindrical polar coordinates, projecting the velocity on the new coordinate axis, so capital U and capital V are radial and tangent, we arrive at this system of equations. I don't know who was the first. My knowledge, I know this paper, right? If you know earlier references of people who have worked on something like that, please let me know. We're currently preparing a paper. So anyway, that's the axisymmetric Boussinesq system that we are solving, numerics in the moving reference frame. To derive the extended quarter-vector phase equation from this system, we look for solutions in the form of these asymptotic expansions. And instead of the slow time variable, which was used by Horikis and others, we use the slow radius time, okay, slow distance time. Psi is the kind of characteristic variable. So at order 1, we obtain this condition, assuming that there are no waves at infinity. At order epsilon, we arrive at this equation for eta 1. That's the cylindrical quarter-vector phase equation, and also this correction to the horizontal velocity, radial velocity, U2. And that's how we introduce the non-locality, right? So compared to Horikis and others, we assume that there are no waves at infinity. So if we define the sum of eta 1 and epsilon eta 2, then for this variable, we can obtain the extended cylindrical quarter-vector phase equation. And this is the slow space version of this equation. And it is actually instructive to compare how the equations look like. So for example, slow space version derived from 2D Boussinesq and slow space version which we also derived from Euler. You can see that all the terms are the same. The difference is in the numerical values of some of the coefficients in the equations. But if we compare with the slow time version or for Euler, derived from Euler in Horacas et al., we see actually that unlike the leading order equations, here there are a few more terms in this version, okay? And we checked, and of course you can go from one version to another. So the slow space version is a shorter version of the equation, and we think that's a natural version in the context of experimental studies when you can put buoys on a certain distance from some origin source, and it's not very practical to think that we can know the state of the system at some moment of time. So in the numerics, axisymmetric Boussinesq equations have been solved for soliton type initial conditions, a squared lambda psi. It turned out to be very important to use the epsilon correction in the velocity. Why? Because in this kind of problems, when you have anything which propagates inwards, because of the cylindrical convergence, it starts growing, right? And it contaminates the numerics very quickly. So you need to get a really close initial condition to be able to do a meaningful numerics. So we use the pseudospectral method for the Runge-Kutta for time stepping. And in order to be able to use periodic boundary conditions, we multiplied the initial condition by a function which tends to zero near the boundaries, and then a sponge layer was inserted into the equations to maintain this, okay? So that we do not really know what is the exact initial condition, say, at the origin of the system, and we can avoid this problem by doing that. So let me show you how this looks like. So the wave starts propagating, and behind the leading wave, the soliton, we see the emergence of some oscillations. And as the wave will start leaving the domain, if you look at the boundary, you can see the structure of these waves. And it certainly also makes sense to have a top-down view. Let's have a look how it propagates. So there is a ring wave, no current, so these are just concentric waves, and they appear a structure behind the lead solitary wave. So now let's have a look at it in more detail. I don't know why it's asking for some confirmation. So this is as a function of the radial variable, and we see that behind the soliton is decaying in amplitude first very quickly, then it slows down and it's further away. This is in the moving reference frame, right? Therefore, in a fixed reference frame, it would be moving very rapidly. There is a shelf behind the wave, and then there is this oscillatory wave trend. Okay. So to do the numerics, there is one further issue, technical issue, that the variables are different, right? So for Boussinesq system, we solve the initial value problem for fixed moment of time. And to initiate the run for the CKDV type models, we need a slice at a constant value of R. Okay, so this was taken numerically, we just take a numerical slice, run the CKDV type models, and then compare at some further distance away. So this is one set of results for epsilon equal to 0.1. We have done from 10 to minus 2, 10 to minus 1, and I will also show you 0.5. Initial condition for CKDV and ECKDV models was placed at capital I equal to 16, and we compare at 20, 100, and 201. On the left, there are the waves, and on the right is the error. So the difference between the numerics for axisymmetric Boussinesq and CKDV and ECKDV. So this is probably the most instructive and easy to read. So the blue is cylindrical quarter vector freeze, the red is extended quarter vector freeze, okay? And at 20 and 100, we can see a very clear indication that extended cylindrical quarter vector freeze is a better model. At 200, we see that there is a significant phase shift, okay? So this is the dependence of the solution on the amplitude parameter on epsilon. And of course, when epsilon is greater, then the waves are faster propagating and the shelf is more pronounced. And that's what happens. This is quite interesting. That's the decay rate of the peak wave for different values of epsilon. And we compared this to the predictions which can be found, for example, in Yuri's paper and his most recent paper with collaborators. So prediction for the amplitude decay from CKdV is -2/3. -1/2 is just linear non-dispersive, and this is linear dispersive, okay? So we can see that for all values of epsilon generated with one and the same values of A and lambda, all of them more or less settle at -2/3 later on. But initially, for smaller value of epsilon, it's probably closer to this. And for greater value of epsilon, it is initially closer to this decay rate. It is possible to have a non-trivial dynamics like in KdV. So for example, here we see fission of a single pulse into two solitons, which then start propagating according to cylindrical quarter vector freeze. So with amplitude decay and all of those features behind the waves. But to get estimates for the number of solitons generated, it is possible to use integrability theory of KdV, Schrödinger equation, spectral discrete eigenvalues, and all that stuff. And finally, that's an extreme case, epsilon equal to 0.5. That's amplitude parameter. And red is extended CKdV, blue is CKdV. And we see that extended CKdV overshoots, CKdV undershoots. The most significant difference is in the shelf, where CKdV has some significant oscillations. Extended CKdV in general performs better than CKdV as well. And that's the dynamics. Let's have a look at the numerics. So the shelf is more pronounced, the greater the amplitude, and as a result, oscillatory wave train is more pronounced as well. So essentially, it is an angular bore, right? We can view it as a step. Once the shelf is generated, we can view it as a step, and there is a step from that level to that. Oscillations naturally develop, and they are rather large here for this value of epsilon. Okay, how much time do I have left?
10 minutes, 12 minutes or something.
Very good. Okay. So why I think it is interesting to consider models of that type. Okay. So let me tell you a little bit about some results for the plane waves. So let us consider the extended quarter vector freeze equation for the plane waves. So for this type of equations, there exist so-called near identity transformations, which were originally developed by Kodama when he introduced these transformations and showed that they can be used to reduce an arbitrary extended quarter vector freeze equation to an integrable member of the family, Fives, integrable Fives quarter vector freeze equation. And later on, Focus and Liu have extended the transformations and showed that with these extended transformations, one can actually reduce the extended quarter vector freeze equation to KdV itself, not just to the Fives KdV. So Marchant and Smythe have used near identity transformations to reduce the extended KDV to KDV, then take some soliton solutions or Angela-Bohr solutions of the KDV, use the inverse near identity transformation, and that way obtain some approximate solution for the extended quarter vector phase equation. Okay. However, KDV doesn't have, for example, solutions like tabletop solitons, which we know Gardner has and strongly nonlinear models have. And we thought that it would be interesting to try to use the near identity transformation to reduce extended KDV to Gardner rather than KDV. Okay, could there be some improvement? And this is what we did in this 2020 paper. Although this was done in the context of solids rather than fluids, but let me tell you nonetheless. So we considered strain waves in a rod. Okay, it's a three-dimensional nonlinear elasticity problem, and the guys are extremely good at numerics, and they managed to do 3D numerics for this solid mechanics problem. At the same time, we derived the extended quarter vector phase equation for the problem using symbolic computations in Mathematica, because derivations are also extremely difficult. And then we use the near identity transformation to reduce the extended KDV, not to KDV as Marchant and Smythe, but to Gardner. Okay? By the way, notice that this is not the Gardner which is obtained from the extended KDV by simply dropping these terms and retaining the cubic nonlinearity term. The coefficient changes, okay? The coefficient is different here. So then Gardner has a known family of soliton solutions. So we take this family of soliton solutions and apply the inverse near identity transformation, and this gives an explicit solution, somewhat long, but elementary functions. And this is an approximate solution to the extended KDV. And so using this, we obtain approximations for all field variables in the 3D elasticity problem. And this is used to initiate 3D numerics. Okay, so this is what was done. And that's the comparison of the full numerical simulations, which is blue, and predictions from KDV and extended KDV. And we can see there are two versions of Gardner, Gardner plus, Gardner minus. This is the Gardner plus version. KDV is green, and there is a significant phase shift. For smaller value of epsilon, red stays on the top of blue as green is left behind. Yeah, but the shape of the waves is very similar. That's Gardner plus case. For greater values of epsilon, red still performs better, significantly better than KDV in terms of the phase shift, but the shape, there is not much difference in the shape of the waves. This is very different when we look at Gardner minus, and that's where we really were hoping to see an improvement. So in the case of Gardner minus, again, we start increasing epsilon, right? So this is a small epsilon, all three curves, KDV, extended KDV, full numerics on top of each other, and we start to gradually increase the value of epsilon, okay? So the KDV is the green curve, and we see that KDV solitons are now a bit narrower. The red curve is essentially on top of the blue for a long time. Yeah, so if this is extended KDV, we further increase epsilon and now come close to the so-called limiting value, yeah, which corresponds to the tabletop solitons, which exist in the Gardner minus case. And now KDV is completely irrelevant. It's very narrow. Blue, not so good as initially, but still much closer to, red is much closer to the blue than green. And finally, when we take the value essentially limiting value of epsilon, The approximate solution develops these funny horns, so the shape is not the tabletop soliton, but if you initiate 3D numerics with this initial condition, it very quickly finds the true tabletop soliton, which is shown here, okay? So my message here, at least in the context of this study, was that the model has worked for greater values of epsilon, and even in the case where we did not expect it to work and it did not work, it still can be used very successfully as a useful initial condition and help you to quickly find the soliton solution. This reminds me a little bit about, something that people do in dynamical systems when they discuss limit cycles, for example. So the true limit cycle is some complicated orbit, but it's often approximated by the nearest circle, right? And then if you initiate numerics with this circle, you quickly find the true limit cycle. So that's somewhat similar. This is not a solution at all, but it knows the correct relation between the amplitude and the speed, so to say, right? Knows something, therefore, numerics quickly find the true solitons starting from that. So we tried to do a little bit in the context of internal waves. That was Ricardo's PhD student who has recently finished. Emilian was an external examiner. And he just tried to look a little bit for solitary waves to do the same in the context of MCC. And this is far from criticality, again, where we don't expect the model to work, and it does not, right? The green curve doesn't look anything at all like the black curve, but the prediction for the amplitude is very close, okay? So hopefully, this needs to be looked a bit more carefully, but hopefully something useful can come from that. So now to CKDV. What is known for CKDV? For CKDV, there is an adiabatic approximation, right, developed by Ostrovsky, Pelinovsky, and Ho and Kuel, where this cylindrical divergence term essentially is treated as a small perturbation, and this gives, for example, this prediction for the amplitude minus 2/3. And interestingly, this is an old paper by Yuri Stepanyans. I didn't know that he has done some experiments in an electric lattice, and he observes these waves and those dependencies on the radius in a two-dimensional electric lattice. Quite amazing experiments. So Robin Johnson has obtained this asymptotic solution starting from quite far from the origin. They must be R0 to minus 1 is treated as a small parameter, but he gave a description further than Ostrovsky and Pelinovsky and Point Curl. So he also has some approximation for the oscillatory wave train. So leading pulse, shelf, oscillatory wave train. And we thought that it would be interesting to compare his solution with the numerics for the Boussinesq. That's for the small value of epsilon, 0.01. So agreement is not so good here simply because of the initial condition, right? So Robin assumes that there is some initial condition which at distance r generates h² profile, right? So I think we need to interpret his results as slow time version rather than slow space version, and then agreement will be better. But his solution is certainly close to the solution of the CKDV equation. CKDV equation, like KDV, is an integrable model. Lux pair was found by Druma and independently by Kalodger and de Gasperis. And there are, for example, these analytical solutions where W is either the first or the second Airy function, and that's from the recent paper of Hurin and Stepanyans. And okay, it's a funny solution, but the pulse agrees very well with KDV soliton and the subsequent evolution in the CKDV equation, but there is this strange shelf to the right of the pulse, okay, which gets smaller. So, okay, this must be understood better, but the leading part of the pulse at least agrees very well, okay? So therefore, it would be highly desirable to obtain Lagrangian and Hamiltonian formalism for CKDV and extended CKDV. Maybe it exists, but I don't know about it. So conservation laws, adiabatic approximation for extended CKDV, near identity transformation, construction of approximate solutions using the known solutions for CKDV, as well as further numerical simulations and comparisons. And I think a lot to be done, and it's a very interesting area. Hopefully, some of you might wish to join. And I would like to highlight that I will give a short course on long nonlinear surface and internal waves on currents from 2D to 3D in an Italian summer school in September in Ravenna. And I'm saying that because it's still possible to apply for PhD students. So maybe some PhD students who are here would like to apply. You can apply for financial support as well. Come to this school. But the deadline is today. Today is the last. Not today, still can do.
Today.
Today. Okay, and these are the references. Thank you.